line of what we're studying in this chapter. And I think last week we already learned the probability mass function and the probability density function, right? Now I want to talk about the cumulative distribution functions. Okay. I will start with the following example. Suppose that x is the number of bits received in error when you transmit 4 bits. Okay. Then x could be 0, 1, 2, 3, 4, and suppose that the probability mass function satisfies the following table, and you want to find the probability of 3 or fewer bits in error. Then you should get the probability that x is less than or equal to 3. Then you get the sum of the probability that x equals 0 and 1, 2, 3. And that sum is simply the sum of the four numbers here, and you get the value 0.9999, right? And that is the probability that x is less than or equals to 3. Okay, and you can use that idea to come up with the following function. I will call it the cumulative distribution function. Okay. So the cumulative distribution function is defined by the probability that x is less than or equals to u, which is the sum of f of k, okay, for all k less than or equal to u, all right? And suppose that we have the following probability function defined by the table, then x could be 0, 1, 2, 3, 4. The second column gives you the probability that x equals k, and the last column gives you the probability that x is less than or equals to k. So 0.35 is the probability that x is less than or equals to 0. 0.57 is the probability that x is less than or equals to 1, which is the sum of the probability that x is 0 and the probability that x equals 1. And then for the value 0.77, you get the sum of the three numbers 35, 22, 20. 0.90 is the sum of the probability that x equals 0, 1, 2, 3. Okay, and finally the sum of all the 5 values give you 1. Okay. So if you draw a graph, you will see that you have 5 values 0, 1, 2, 3, 4, and the corresponding columns gave you the probability that x equals k. Okay, and the sum of the three values at 0, 1, 2 give you the probability that x is less than or equal to 2. Okay, and the sum is called f of 2. So I would say that this is f of 2. Okay, and I would say, and this is going to be f of k. So f of k, where k equals 0, 1, 2, 3. Okay. Do you understand? Is that okay? All right. that is a discrete random variable. What if you have a continuous random variable? If you have a continuous random variable, then you don't have a probability mass function. Instead, you will have a cumulative. You will have a probability density function. And then you need to use the density function to define the cumulative distribution function. So you come up with this one. So that is the probability that x is less than or equal to u, which is the integral from -infinity to u ft dt. All right. And if you have a look at the first graph, you have a blue curve, which is the density function. All right. And then you compute the integral from -infinity to u. You should get the area of the blue region, which is the probability that x is less than or equal to u. Okay. And then you can then based on that you can draw the graph of the capital F of u. The function capital F of u is a continuous function which is increasing, right, from 0 to 1. Then that is the red one. Is it okay? Is that all clear? Okay. All right. Now I will move to the next example, showing a little bit more details about the cumulative distribution function. Okay. Now suppose that x is the number of defective parts in the sample up to two items, just like when you select two parts randomly from a part from a set of 850 parts containing 50 defective parts. And then you want to find the number of defective parts in the sample of two parts. Then x could be 0, 1, 2. Okay. If you learn the hypergeometric distribution, you will see that the probability that x equals 0, 1, or 2 should be 0 0.886, 0 0.111, and 0 0.003. Okay. And based on that, you can get the following functions.
Teacher,
Yes.
I think that our class have study to standard deviation already.
Oh, really? Let me check, because when I check, I just thought that we just finished the first session. Are you sure we already studied the standard deviations?
Yes. On Saturday you
Oh, okay, I see.
a makeup class, so that we.
Oh, I see. Let me check. Hold on. Okay, thank you very much. So I think I'm going to stop on the recording, and then I'm going to record a new one again. And I'm going to upload the new one so that it's easier for you to watch it. Yes, I will upload the recording. Okay, so let me remind you what we have learned so far. I think we already learned the probability map function and the probability density function, right? We also learned the cumulative distribution function. Based on them, we can define the mean value of x, right? We can define the median of x. Understand? And then I already mentioned about the variance. Okay, so the variance of x is the mean value of x minus m squared, where m is the mean of x, right? That is the definition of the variance of x. And then we can also we can also have the definition of the standard deviation of x, which is the square root of the variance of x. Okay. Now I wanted to discuss a little bit further about some properties of the variance. First of all, I want to remove the parentheses here to get the mean value of the x squared minus 2mx plus m squared. Okay, and that is the mean of x squared minus 2m times the mean of x plus m squared. Okay, and you see that this is the mean of x squared minus 2m times the mean of x, which is m. So this is 2m squared plus m squared. So I can say that the variance of x is simply the mean of x squared minus m squared. Do you understand? Is that clear? Is that all clear, you guys? Okay. Okay. Then you get this formula, right? You have this formula. The variance of x equals the mean of x minus the mean of x squared minus the square of the mean of x. Okay. That is the first thing, the variance of x. Now you want to talk about the variance of the ax plus b. What do you get? Okay, let's have a look at this. Suppose that there are 4 observations, 1, 2, 5, 8, and then you get 4 values with the mean value 4. Okay, and then I consider x plus 1. This is x, and this is x plus 1. Then x plus 1 gives you 2, 3, 6, and 9, right? And you subtract, and then you compute the mean value. You will get 5, and then you can compute the deviations All right. So you still get 2 minus 5, which is minus 3. And then you still get minus 3, minus 2, 1, 4 for the derivations. It means that the variance of x plus 1 is the same as the variance of x. Okay, because if you just like you move the distributions to the or the observations to the right 1 unit, the everything we've changed except the derivations, and because the derivations are the same, the variations should be the same. So I can say that the variance of x plus b should be the same as the variance of x. Okay, which means that the variance of b, a constant, should be 0. How about the variance of ax? The variance of ax, you can have a look at this. If you have a here, that should be a squared, and then m squared gives you a squared as well. So you can factor the common factor a squared out to get the variance of ax is equal to a squared times the variance of x. Then from these two equations, I can conclude that the variance of ax plus b is simply a squared times the variance of x. Do you have any questions? Okay. Okay, good. For the sum x plus y, you need one assumption that x and y are independent. That I will mention further in the next part of this chapter when we learn random vectors. Okay. So this is the summary of what I just mentioned. The variance of x is the same as the mean value of x squared minus the square of the mean of x. The variance of ax plus b is a squared times the variance of x. And if you apply the square root on the both sides of this equation, you should get the standard derivation of ax plus b is equal to a times the standard derivation of x. In addition, if x and y are dependent, then the variance of the sum x plus y is equal to the variance of x plus the variance of y. Okay? Any questions so far? Is that all clear? Good. All right, let's consider this example again. If you have a look at the table, you will see that we have the first two columns. The first column gives you all the values that a random variable may take, and the second column gives you the task, right? The corresponding probability. Then you can find the mean value. You can find the mean value, which is 0.4. You can also find the variance of x, which is 0.36, right? Okay, that is what I mentioned last time. Now I want to talk about the last column. What is the last column? The last column gives you 0.52. What is 0.52? 0.52 is the sum of x squared f of x, and that is simply the mean value of x squared. Okay, the mean value of x squared, and you can use the formula I just mentioned. Which one? This formula. The variance of x is the mean of x squared minus the square of the mean of x. The first term is 0.52. The second term is the square of 0.4, and this is again 0.36. So this value is the same as that value, right? Is there any question so far? Okay, now get back to the example of the current in a thin copper wire. Then you can get the probability density function f of u equals 0.05 for u between 0 and 20. And then you want to find the mean and the variance of x. It is easy to find the mean, right? The mean of x is simply the integral from minus infinity to infinity, u times f of u. And that would be the integral from 0 to 20 of the function u times 0.05. Because the function is non-zero within the interval 0 to 20, and it is 0 outside the interval. That's why you only need to integrate from 0 to 20. And within the interval 0 to 20, the function f of u is 0.05. Then altogether, you can find the mean value, which is 10. After you find the mean value, you can get the variance of x by integrating the function u minus m squared. Here, m is 10 times f of u, and you integrate from minus infinity to infinity. And again, the function fu is only non-zero within the interval 0 to 20. So you get the integral from 0 to 20, u minus 10 squared times 0.05, where 0.05 is the function f of u, okay, within the interval 0 to 20. And then you can integrate the function by using the calculator, or you can do the calculation by yourself to get 100 over 3. And then you can find the, that is the one way to get the values of x. You can also find the values of x by using this formula, in which you need to know the value of the second moment mean of x squared. So I need to find the mean of x squared, which is the integral from minus infinity to infinity, u squared f of u du. And that integral is simply 400 over 3. And you use the formula to get 400 over 3 minus 10 squared. And it is the same as 100 over 3. Okay? So you see that these two numbers are the same. Is that clear? Is that all clear? Okay. Now I want to move to the next example. Suppose that there are four distributions. X1 is the right one. The right one, the blue one, you call it what is that? The X2, and then you have X3, and you get X4. Now, please tell me, which one gives you the greatest value of the mean plus the standard deviation? Can you tell me about that? Which one gives you the greatest value? You think about that for a minute. Do you get that? Do you get it? It's in X4. Okay. How about the others? X3 give you greatest mean. X2 and X4 give you greatest standard deviation. Okay. Concerning the mean value, you will see that the mean value is used to describe the center. Okay. So the mean value it can be used to describe the center of the whole data set. Okay, of the distribution. So you see that the the mean value of x2 and x4 equals 0 right here. Okay, so the mean value of x1 and x2 are the same. Okay, the mean value of x3 and x4 are the same. Okay, and because the mean value of x3 and x4 is 30, and that is greater than 0, which is the mean values of x1 and x2. Okay. Concerning the standard deviation, or the variance could be used to describe the variation of a distribution. So if the a distribution looks fatter, bigger, right, and then the variation should be greater, and the variance should be greater, or the standard deviation should be greater. Therefore, I can see that the variance, or let's say the standard deviation of x2 and x4, they have the same shape. Therefore, they should have the same variation, and they should have the same standard deviation. So I get this. Okay. The standard deviation of x1 and x3 uh, are the same because the red and green distributions have the same shape, so they have the same standard deviations, and then and you see that because the red and green distributions look thinner, so um, they have smaller standard deviation. So if you have a look at these two inequalities, you can conclude that x4 will give you the greatest sum. Is that clear? Do you understand? Okay. Okay. Now, can you find the variance of the and also the mean value of the following random variable? Do you know that? Okay, so you conclude that the mean is 0 and the variance is 4/15, right? Okay. First of all, I need to find the value of c. Then I get 1 equals the integral from -1 to 1 c 1 minus u squared du, right? So I get c u minus u to the third over 3 from -1 to 1. And then you get c times, what's that? 1 minus 1/3 minus minus 1 plus 1/3. Okay, so you get c times 2 minus 2/3, and the answer will be 6 minus 2, we get 4. So you get 4c over 3. Okay, so c is simply 3 over 4. And then you are ready to find the mean value of x. The mean value of x is the integral from -1 to 1 of the function u times f of u du. Okay, and you get the integral from -1 to 1. U f of u is 3/4 times 1 minus 1 minus u squared du. And because this function is an odd function on the interval -1 to 1, so that integral is 0. Okay, and then you can find the mean value of x. In order to find the variance of x, you need to find the mean of x squared, the second moment. So you get the integral from -1 to 1 u squared f of u du. And that is the integral from -1 to 1 u squared times 3/4 1 minus u squared du. Okay, is there any question so far? Is it all right? And then you can find the variance of x, which is the mean of x squared minus the square of the mean of x. Okay. That's clear. Okay. Okay. All right. So let's move on to So I think we just finished this the almost the first the first few parts of this chapter concerning the random variables. Now I will move to the last one of the chapter, John probability mass function. So what we have learned so far includes a random variable. Okay. But what if we don't have a single random variable? Instead, we can have many random variables, like x and y. Okay, x and y. For example, you can when you study the effectiveness of a vaccine, you need to learn not only the age of the patient, but also um, but also um, but also the gender of the patients, right? And maybe you may need to study the location of that patient. Okay, so that are things that you want to learn about that patient. Okay, or is that a healthy people? Is that a healthy person or a sick person? There are a lot of information you need to collect. Okay, at the same time, that's why we need to consider kind of factor, not a single variable. Then let's say we get x and y, and this vector is called a random vector. Okay, we have a random vector, and in order to describe the the distribution of the random vectors, you still need to know about the values, all the values that the vector may take, and also the chance that you can observe on those values. Okay. And because you get a vector, then you need to come up with something like the probability that this vector, let's say z, z is equal to another vector. Let's say vector z0, for example, and then you can come up with a simpler description, which is the probability that x equals u, and then y equals v. All right, where z0 is the point u and v, and then the capital Z is the vector x and y. All right, is there any question so far? Any questions? Good. Okay. And you call it the Proxima function, the John distribution of a random vector, and you denote it by f of uv. So f in this case is a function of two variables instead of one variable. All right, and you call it the John Proxima function of a distribution. Okay. This is what you get. The Proxima function of x and y satisfies this equation f equals probability that x equals u and y equals v. And then the function f is greater than or equal to 0 for all uv, and the sum of the function f of uv for all u and v should be equal to 1. Okay, let's consider the following example. Okay, now suppose that there are two random variables, x and y, and you get the random vector x, y, where x is the number of bonds of signal strength and y is the response time. Okay, then you get the table. If you have a look at the table, you should understand it this way. 0.01 is the probability that x equals 1 and y equals 1. 0.02 is the probability that x equals 2 and y is 1. 0.25 is the probability that x is 3 and y is 1. Okay. 0.02 is the probability that x is 1 and y is 2. 0.03 is the probability that x is 2 and y is 1. Okay, and so on. And then you have all the numbers here, and you compute the sum of all the numbers. You should get 1, and that value 1, right? You get the value 1 right here. Okay, so that's why I said the sum of f of u v should be 1. Okay, now you find the sum of all the numbers along each row to get 0.25, 28, 25, 8, 17, and 30. All right, all the numbers here will give you a so-called marginal distribution of y. Okay, and all these numbers here, when you can obtain, you can get them by adding all the numbers down each column. And as you get 0.2, 0.25, 0.55, they will give you the probability that x equals 1, 2, or 3, and you call them and you call them the probability mass function. I'm sorry, the marginal distribution of x. Okay, so what I'm saying is that the probability that y equals 1 is 0.28. And for this, you get the probability that x equals 1 is 0.20. Okay? Do you understand? Is that clear? Is that all clear? Okay. Now I want to talk about the probability that question A. What is the probability that x is less than 3 and y is less than or equal to 2? What do you think? It should be the probability that x is less than or equal to 3. X is less than 3. X is less than 3 if x is 1 or 2. Okay. Y is less than or equal to 2 if y is 1 or 2. Then you come up with the 4 values here. All right. Then this is 0.01 plus 0.02 plus 0.02 plus 0.03. And then you get 0.08. Do you understand? Okay. Question B. What is the probability that x is less than 3 given that y is less than or equal to 2? What do you think? It should be the probability that x is less than 3 and y is less than or equal to 2 divided by the probability that y is less than or equal to 2, right? What is the numerator? The numerator is 0.08, I think. And the denominator is the probability that y is less than or equal to 2. Y is less than or equal to 2 gives you 0.28 and 0.25. So I get 0.28 plus 0.25, and then you get 8 over 53. Is that clear? Okay. For the last question, the probability that y is less than or equal to 2, given that x is less than 3, you can use similar arguments to see that it is basically 8 over 45. Okay, you can double check on that. Do you understand? Is that clear? All right. Finally, what I mentioned, this is what I mentioned about the marginal distribution. You get f of u is the probability that x equals u. And then you need to sum all the numbers, right? You need to find it here. So based on the if you have a look at the table here, you can see that you have x could be 1, 2, 1, 2, 3, and then you come up with the fx, which is 0 0.2, 0 0.25, 0 0.55, and this function f of x is called the marginal the marginal probability distribution for x. Okay, and that would be fxu. Okay. In this chapter, remember that in this chapter we only study the discrete random variables, random vectors. Then we get this is what we get. We have the marginal distribution for x, right, from here. and the marginal distribution for y. Okay. Now we are ready to compute the mean and the variance of x and y. What's the mean and the variance of x and y? In order to find the mean of x, you need to use the marginal distribution of x. So you come up with this one. Okay. Then I get x. Then you get the following mean value for x, which is 1 times the probability that x equals 1, plus 2 times the probability that x is 2, plus 3 times the probability that x is 3. And then you get 1 times 0.2, plus 2 times 0.35, plus 3 times 0.55. Okay? Do you understand? So you get 0.2 plus 0.5 plus, what is that, 1.65. Okay? And then you come up with 0.7 on 2.35. Okay? That is the mean of x. And if you want to find the mean, the variance of x, you need to find the mean of x squared. The mean of x squared is 1 squared times 0.2 plus 2 squared times 0.25 plus 3 squared times 0.55. Okay? And after that, you can find the values of x, which is the mean of x squared minus the square of the mean of x. Okay? Is there any questions? Is that all clear? All right. So if you you have no further questions, let's have a break. Then after that, we will move to the next chapter of some special distributions. Okay.
Từng ngày dài còn lại một mình nơi đây, nhìn cánh chim bay ngang thấp thoáng trời xa, lòng ngậm ngùi về một cuộc tình đã lỡ, tình đã bay nhớ.
Including binomial distributions. So we talk about that. We will learn binomial distribution. We will learn Poisson distribution. We will learn a little bit about the uniform distribution. Normal distribution. All right. Okay. And then I will talk about the central limit theorem. Okay. Did you watch the video about some special distributions? Did you watch video about that? Are you sure about it? Let me check. You should be able to find them on the video website. Let me check. Oh, I see. Equals hidden from students. Okay, that's fine. I'm going to upload the video again, and then you should be able to watch them. So what is a binomial distribution? What is that? What is a binomial distribution? A binomial distribution is used to describe the number of successes in n trials. Okay, in n trials. But this is what I'm saying. Okay, so a binary trial is a trial in which you can win or you lose. All right, 1 means you win and 0 means you lose. You are winning with probability p and you are losing with probability q 1 minus p. It is very easy to prove that the mean value of z is p and the variance of z is p times q. All right, you can verify that very easily. Then a binomial random variable is the number of successes in n Bernoulli trials. For example, there are 20 independent items with defective rate 5%, and you count the number of defective items among them. That number is a random value, right? A random variable, and it is called a binomial random variable. Or you can count the number of winning tickets among 11 independent lottery tickets with the winning rate 1%. Or you can use it. You can use binomial distribution to describe the number of patients reporting symptomatic relief with a specific medication with the effective rate 80%. Do you understand? And we use the notation x follows a binomial distribution NP. Okay, like in the first example, x is the number of defective items among 20 items. Then you will say that x follows. When I use the notation tilde, I want to say that x follows a distribution. X follow the binomial distribution. B stands for binomial. 20 items with the effective rate 5%, so you get 0.05. Okay. If in the second example, if x is the number of winning tickets, then x follows a binomial distribution with the mean with the value n is 11 because there are 11 lottery tickets. They are independent, and the winning rate is 1%. In the third example, x is the number of patients reporting symptomatic relief, and x follows a binomial distribution with n we don't have it here. So let's say there are some patients in the experiment, and the effective rate is 80%, so you get 0.8. Do you understand? Is that all clear? Okay. Again, well, this is just give you example about x. This is the example. You just count the number of items. Maybe we can move on, and then you will see the main idea when we try to solve some problem. It's just like you play several games. You play 10 games, right? You play 10 games and you count the number of games that you can win. That number of winning games is a random variable, and you call it a binomial random variable. That's all. Do you understand? Is it okay? All right. Then you can have then you can come up with the following results. First of all, I want to talk about the distribution. How can you get the distribution? In order to get the distributions, I need to know the values that the random variable x might take. So suppose that x follows a binomial distribution NP. Okay. And then x follows a binomial distribution with the two parameters n and p. Then x can check the values 0, 1, 2, and then n, right? So x can take n values, can take the values from 0 to n, because you play n games. Do you understand? Okay. And now you want to find the probability mass function. You want to find the probability that x equals k. Okay. Is that clear? Is that all clear? Now, what is the probability that x equals k? The probability that x is equal to 0. What is that? The probability that x equals 0 is the probability that you win no game, or let's say you lose all games. You lose all games, it means that you lose the first game with the probability q. You lose the second game, which is q. The probability that you lose the third game is q. The probability that you lose the last game is q. Then you get q to the n. Understand? You can find the probability that x equals 1. What is that? Let's say n. N is the probability that you win all games. So you win the first game, you win the second game, you win the third game, you win the last game, and you get p to the n. All right. What is the probability that you win exactly one game? If you win the first game, then what is the probability that you win only one game, which is the first game? The probability that you win only one game, which is the first game, is the probability that you win the first game and you lose the others. So you win the first game and you lose the others, q to the n minus 1. All right. And then that is the probability that you win the first game and you lose the others. What is the probability that you win the second game and you lose the others? The same thing, right? The same values. Then altogether, you can see that you get n choose 1, p times q, n minus 1. In general, you can see that the probability that x equals k is simply n choose k, p to the k, q to the n minus k. Do you understand that? Do you understand? Okay. All right. For example, let's go back to the first example. Suppose that there are 20 independent items, and you select, and then you count the number of defective items. Then what is the probability that there is exactly one defective item among those 20 independent items? Then you want to find the probability that x equals 1. And then you should get 20 choose 1, and then 0.05 to the first, and then 0.95 to 19. Do you understand? Do you understand that? Okay. Okay. Then you can well, now let us consider a little bit further the case of binomial distribution. Suppose that you have x follows a binomial distribution NP, and then x1 is 1 if you win the first game, and 0 if you lose the first game. x2 is 1 if you win the second game, and 0 if you lose the second game. x3 is 1 if you win the third game, and 0 if you lose the third game, and so on. So you get up to xn. And then it is obvious to see that x is x1 plus x2 plus xn. Do you understand? Okay. And then you want to find the mean of x, which is the mean of x1 plus x2 plus xn. Okay. And you get the mean of x1 plus the mean of x2 plus the mean of xn. So the mean of x1, as I mentioned before, the mean of xi is p times is p, and the variance of xi is p times q. Okay. The mean of x1 is p, the second is p, and then you get p. All right. So the mean is n times p. For the variance of x, you get the variance of xi, s1, plus x2, plus xn, and that would be the variance of x1 plus the variance of xn. And each variance is p times q. So you get npq. Is that clear? Okay. Then go back to this. Go back to this. You get x follows this binomial distribution 20, 0.05. Then I can say that the mean of x is 20 times 0.05. And you get, is that 0.5 times 2, so you get 1, right? And the variance of x is n times p times q, so you get 20, 0.05, and then 0.95. That makes sense? Okay. Now let's have a look at the following graph. Then you can have some idea about the distribution. All right, so if n is 8 and p is 0.5, then the distribution is quite symmetric. It's symmetric, right? P is 50%, then you get a symmetric distribution. If P is 20%, then you have you will have a skew distribution. Okay. And again, if n is 30 and P is 50%, then the distribution is still symmetric, right? You can see that. If P is 20% and n is 30, then the distribution, even though it is still skewed, it is a little bit more. It is a little bit more more symmetric. It looks more symmetric to us, right? If you compare this one and that one, then the second one looks more symmetric, and that's why later you will see that if n is big enough, then the distribution will look more symmetric. In fact, it will look it looks more normal. Okay, and then you can come up with the central limit theorem. Okay, that is a story. Okay, let's consider the following example. Each sample of water has a 10% chance of containing a particular organic pollutant. Assume that the samples are independent with regard to the presence of the pollutant. Find the probability that in the next 18 samples, exactly 2 contain the pollutant. Can you do that? Do you know how to get that? Okay. Let's give it a try. I suppose that x is the number of samples that contain a pollutant. Okay. Then you get x follows a binomial distribution, 18, and then you get 0.1 for this, and then you want to find the probability that there is exactly 2. Okay, and then you come up with the probability that x equals 2. That is 18 to 2, 0.1 squared, 0.9 to the 16. Okay, for question B, you want to find the probability that there are at least 4 samples containing the pollutants. So x is at least so greater than or equal to 4. So it should be 1 minus the probability that x is less than or equal to 3. And then you get 1 minus the probability that x equals 0. X is 1. X is 2. X is 3. Then you get 1 minus 18 to 0, 0.10, 0.9 to the 18, right? And you keep doing that, 18 to 1, 0.1 to the first, 0.9 to the 17, okay, something like that, and you can get the answer. All right, makes sense? And if you want to use R, what do you get? If you want to use R, then it should be 1 minus the value you want to deal with is 3, right? And then n is 18 and p is 0.1. Then you come up with, wait a minute. What is the answer? Do you know that? Oh, it should be by right now. It should be it's 0.098196, right? Do you get the same value? Do you get the same value or not? Okay, makes sense? Okay. Now let's move on to the next example. Question 2. Do you know how to solve the problem? So what do you get? Now suppose that X is the number of components that have failed, okay? Then you see that X follows a binomial distribution because there are 10 components, right? And the probability that each component will fail is 20%, correct? And they are all independent, okay? Now you want to find the probability that at least one of the components has, you want to find the probability that at least two of the components have failed, at least two. So you want to find the probability that X is at least two. Given that, then you have conditional probability. At least one of the components has failed. So you get X is greater than or equal to 1. Okay? Do you understand? Then you get the probability that X is more than 2 and X is greater than or equal to 1 over the probability that X is greater than or equal to 1. And then you get the probability that X is greater than or equal to 2, because more than 2 and more than 1 is equivalent to that X is more than 2, right? So you get the probability that X is greater than or equal to 1. Okay? Do you understand? And this is 1 minus the probability that X equals 0 minus probability that X equals 1. Okay? Do you understand? Is that clear? Is it okay? The answer would be 0.69927. All right? Makes sense? Okay. Let's try the next example. Okay, so in this case, x is the number. X is the number of the number of bits received in error. Then x follows a binomial distribution with n is 6 because you transmit for 6 bits, and then the error rate is 10%. So, and you want to find the mean of x, which is 6 times 0.1, and you get 0.6. Okay. All right. And then if you want to find the variance of x, then that would be 6 times 0.1 times 0.9, and then you come up with what is that? 0.54. Okay. Is that clear? All right. So I think that that is about the binomial distribution. Now I want to move to the perhaps let me give you one example, one application of binomial distribution. Think about the COVID-19. Remember, suppose that we try to we have many people in a population. All right, let's say we have 1,000 people, and you want to test whether they are affected by the COVID-19, a kind of a disease, for example, COVID-19. What can we do? One way to do it is to test them all. Test all 1,000 people. Okay. Then how many tests do you need? How many tests do we need? You need exactly 1,000 tests to do it, right? Another way to do it is to test. Not 1,000, all 1,000 people. We try to combine. We try to decompose the whole population into several subpopulations. So let's say you get suppose that there are n subpopulation. Okay, suppose that there are n subpopulations. And then you come up with there are n subpopulations, and then you come up with the in each subpopulation there are m people. So let's say with each subpopulation has m people or m members, right? Understand? So let's say there are n groups, and each group has n people. So I have the equation capital N equals n times n. Okay. On the other hand, I try to combine their samples. Okay, I try to combine their samples. So I come up with a single sample, for each group, right? And I try to test those samples. So how many tests do we need at that time? There are only n subpopulations. Then we only need to test. We only need little n tests. All right. So we need to perform n tests. Okay. This little n is much smaller than the capital N. Okay, that is the first step. The second step, if all of them are negative, then you don't need to do anything else, right? If some of them, okay, if a combined sample give you a positive result, then how many tests do we need? Then we need one. Then we need m tests, right? Then we need m tests. Make sense? So at the beginning, we need little n tests for any positive group. You need additional m tests. That makes sense? Okay. Then if you are lucky, and you divide the whole population into, let's say, only 10 groups, all right, or let's say 100 groups. Suppose, for example, if n is 100 and little m is 10, so there are 100 groups. Each group has 10 people, and you are lucky, then you only need to perform 100 tests instead of 1,000 tests. Do you understand what I'm saying? Is that okay? And it could save a lot of money and effort and time. Do you understand? Is that clear? All right. So here's my question. What is the optimal value for n and m? What are the optimal values for n and m? Do you know them? Can you do that? How can we do it? Now, we need we need one more assumption. We need the assumption that P is the probability that that a person has the disease. Okay, and then I will denote by x. I will denote by x. By x, let's say by x, the number of people in a group who have the disease. Okay, and then I denote by y the number of groups, I would say, with positive results. Okay, and you have to retest the whole group, right? Makes sense? Then how many tests do we need? How many tests do we need? At the beginning, you only need to test little n, right, group. So you need only n tests. For any additional group, for any positive group, you need little m tests. For any group, additional group with positive results, you need little m tests, right? Because each group has m people. Then you get m times y, correct? You have m times y, where y is the number of groups with positive results. That y is the number of groups, and m is the number of people in each group. Do you understand? Is it okay? Good. So you want to minimize it. I want to minimize it because I want to minimize the number of tests. So I get or let's say the mean of z, because you don't know the value of z. Z is a random variable, so I want to minimize the average value of z. In order to do that, I need to know the mean value of z, which is n plus m times the mean of y. And what is the mean of y? What is the mean of y? The mean of y, in order to find the mean of y, you need to know the distribution of y, right? You need to know the distribution of y. Y is the number of groups with positive results among n groups, right? So y follows a binomial distribution with the two parameters n and let's say p1, okay, n and p1, where p1 is the probability that a group has a positive result. Okay, if you know n is given, if you know p1, then you can conclude that the mean of y is n times p1. Makes sense? So it is remaining to find the value of p1. What is p1? P1 is the probability that a group has a positive result. The group, this group, each group has a positive result if there is at least one person, one member of the group has the disease, right? So P1 is the probability that the number of people with the disease in the group is greater than or equals to 1. So it is the probability that x is greater than or equal to 1. Do you understand that? And that is 1 minus the probability that x equals 0. Now, in order to find the probability that x equals 0, you need to know the distribution of x. What is x, by the way? X is the number of people in a group who have the disease. And how many people are there in each group? There are m members, right? Correct? So x, in this case, you can see that x follows a binomial distribution with the parameters m, p, right? Because there are m people in that group, and the probability that each person has the disease is p. So x follows a binomial distribution. Then this becomes 1 minus c m to 0, right? Because x follows a binomial distribution with two parameters m, p. Then you get p to 0, 1 minus p to the n, right? And then you get, you have this equation, you have the value of p1, which is 1 minus, basically 1 minus p to the n. Do you understand? All right. Now I will plug everything back to this expression to get the mean of z. What is the mean of z? The mean of z is n plus m times the mean of y. The mean of y is n times p1. So you get n times p1. And p1 is this expression, 1 minus p to the n. Do you understand what I'm saying, everyone? Is that all clear? Okay. Then I come up with m times n is capital N. All right, so that is very easy to observe. What is n, by the way? N, this n is capital N over m, so I get capital N over m plus capital N times 1 minus p to the m, okay? And then I get capital N times 1 over m plus 1 minus p to the m, like that, okay? And you have this, I denote by gm this equation, this expression, all right? So I get the function gt, which is 1 over t plus 1 minus p to the t. P is given, all right? P is the probability that a person has the disease, or let's say the relative frequency of people with the disease in the population. All right, so you can get this value very easily from the media, right? You can Google that information, and then you have a function like this one. How can you get the optimal value? You want to minimize the function gt. If you want to minimize that from what you learned in calculus 1, I hope that you still remember that. You need to differentiate the function gt, and you let it be 0. So you get minus 1 over t squared minus, what is that? 1 minus p to the t times the logarithm of 1 minus p, correct? And you let it be 0, and you can solve for t. You can use the calculator, or you can use the computer for that, okay? Or if you already learn numerical analysis, numerical method, then you can also write programs to do it. But I think this is very simple, so you don't need to write a program by yourself. You can use MATLAB to get the answer. Is that all clear? Do you understand that? And then you can get the optimal value for this case. Is that clear? Do you understand? Here we have the assumption that the effectiveness of the test it isn't changed even if you have many even if you have combined samples. It is not really correct in reality. That's why the value of 10 here is not the real. It's not really the optimal value, because we didn't take care of the effectiveness of the test when we increase the sample size. But that gives you some idea about the number of about the optimal value. All right. Any questions so far? May I move on? Okay. Now I want to talk about another distribution, Poisson distributions. A Poisson random variable is the count of events that occur within an interval. Okay, and for example, you can use a Poisson distribution to describe the number of cars across the street every minute, or you can count. You can use it to count the number of photons arriving at the telescope every minute, for example. So you can come up with the following applications. Some applications of Poisson distribution. You can use a Poisson distribution to describe the number of mutations on a strand of DNA per unit length, the number of bacteria on some surface or width in the field, the number of customers arriving at a counter or call center in 10 minutes, something like that. Okay. So it should be the number of events that you can observe during a period of time or within a region. The sample space should be the set. The set of all the possible values that a random variable may take would be 0, 1, 2, 3 up to infinity. And then you have the following probability mass function. The probability that x equals k is the exponential of minus lambda times lambda to the k over k factorial. We take the expression for granted. If you want to prove it, then you can have a look at the limit here. I put it here for your information if you really need the explanation. Okay, and you can come up with a limit here, and you get the probability mass function. But I don't want to spend time on that. We just use it, and then you have this formula, is the expression for the probability mass function, and then you can use the definition of the mean value and the variance to get the formula for the mean of x and the variance of x. The mean of x is simply the sum k from 0 to infinity, k times f of k, which is e to the power lambda minus lambda to the k over k factorial. And if you remember what you learned in calculus 1 regarding the Taylor expansion, then you should be able to find and series. Then you should be able to find to compute this sum, right? And you can prove that this sum is simply lambda. So the mean value of x is lambda, and you can also use similar arguments to get the value of variance. And it is very interesting to observe that the variance of x is also lambda. So in a Poisson distribution, the mean of x and the variance of x are the same. They are all lambda. Do you understand? Okay. So I can say that x follow a Poisson distribution with only one parameter, lambda, and lambda in this case is the mean value of x. Is that all clear? Is that okay? Is that okay? And besides, if x is the number of, suppose that x1 is the number of x of red cars across the street every minute, x2 is the number of blue cars, x3 is the number of white cars, then you can consider x1 plus x2 plus x3, and suppose that they are independent, then this sum gives you the number of cars crossing the street with the color red, blue, and white. Okay, and that sum also follows a Poisson distribution because it's just the number of cars crossing the street every minute, right? And you have lambda. This lambda is simply the mean value. So I get lambda is the mean of x, and that is the mean of the sum, right? And then you get the sum of the means, and then you get lambda 1 plus lambda 2 plus lambda 3. Therefore, if you have therefore you have the following result. If xi follow a Poisson distribution lambda I, and there are independents, then the sum of xi follows a Poisson distribution with the parameter lambda equal the sum of lambda I. For example, if x1 follows a Poisson distribution with the parameter 2, and x2 follows a Poisson distribution with the parameter 3, and they are independent. Okay, they are independent. Then we can conclude that x1 plus x2 follows a Poisson distribution with the parameter 5, right? Do you understand? Is that all clear? Okay. You may want to have a look at the graph of some Poisson distribution. For the first one, lambda is 0.5, and the distribution is heavily skewed. Can you see that it is heavily skewed? If lambda is 5, then it is still skewed, but a little bit less skewed, right, compared to the first one. And then if lambda is 20, then the distribution is still skewed, but well, it's really hard to recognize that, right? It looks more symmetric and almost symmetric. And again, like the Poisson the binomial distribution, a Poisson distribution looks more normal, more symmetric when the parameter lambda is big enough. Okay, and then we will go back to that in the last part of this chapter, the central limit theorem. Is that okay? Do you understand? Let's consider the following example. Consider an experiment that consists of counting the number of alpha particles given off in a 1-second interval by a 1 gram of radioactive material. If we know from past experience that on average 3.2 such alpha particles are given off, what is a good approximation to the probability that no more than 2 alpha particles will appear? Do you know how to solve the problem? Is it okay? All right. In this case, suppose that x follows a Poisson. X is the number of alpha particles given off in 1 second. Then X follows a Poisson distribution with a parameter lambda, where lambda is on average 3.2. So you get 3.2 here. Okay. So you get, I should say, lambda with lambda equals 3.2. And then you want to find the probability that X no more than 2, so less than or equal to 2. Then you get the probability that X equals 0 plus X is 1 plus X is 2. And then you get the exponential. The formula is, what is the formula? Exponential lambda to the k over k factorial. That is to say, the exponential minus lambda, which is 3.2. And you get 3.2, 0 over 0 factorial plus 3.2, 1 over 1 factorial, 3.2 squared over 2 factorial. Is there any questions so far? Is it okay? Do you get it? Yes? Okay. Let's try this example. What did you get here? Suppose that X, question A, X is the number of flaws in 1 millimeter of wire. Then X follows a Poisson distribution with the parameter lambda is 2.3. Then you want to find the probability that X is exactly 2. And then you get, it is, what is that? The exponential minus 2.3, 2.3 squared over 2 factorial. Understand? Is that clear? Do you get it? How about question B? For question B, you want to find the probability of exactly 10 flaws in 5 millimeter of wire. Then suppose that Y is the number of 10, the number of flaws in 5 millimeter of wire. Then Y follows a Poisson distribution with the parameter lambda. What is lambda? Lambda is the number of flaws in 5 millimeter of wire. Be careful, it is 5 millimeter of wire, not 1. So in 1 millimeter of wire, you observe 2.3 flaws on average. Then in 5 millimeter of wires, you expect to observe 2.3 times 5, right? And you get 11.5 flaws. Then the probability that Y is 10 is basically the exponential minus 11.5, 11.5 to 10 over 10 factorial. Do you understand? That clear? For the first question, here's the results you get. On 0.5960. For the second problem, what do you get? It is 10 and you get 11, 5, and you get 0.4. Is it okay, you guys? Any questions so far? Oh, I think I used the wrong function. Sorry about that. I think I used the wrong function. It shouldn't be p. It should be this. I think wrong. P. I used the wrong one. It shouldn't be p. It should be d. D stands for the value of the function, the distribution. P stands for the probability cumulative distribution function. So we were not going to use to find the probability that actually less than or equal to 10 and want to find the probability that actually is equal to 10. So I should use D for that. So it should be this. And I come up with this one, I think. So for the first one, it should be 0.2652. For the second one is 0.112935. Any questions so far? Is that clear? Okay, so I think that's enough for today. Let's stop here and see you next time. Now, we will not learn geometric and hypergeometric distributions in this chapter. Is it okay? Yeah. and there will be a quiz for you to do. Right, and please double check the calendar later to do the quiz. Okay. Do you have any questions so far? Good. All right. Thank you very much. Thank you and goodbye.